Hi everyone, my name is Pinchen. I'm a PhD student at the Penn State University, and I'm also a visiting student at the University of Toronto. So today I'll be talking about how we can detect extraterrestrial civilizations that use a deep space network that's similar to ours. So the problem that we're trying to solve is with this. So SETI is easy if you know when and where to look. Basically, if you call the aliens and ask when they will be transmitting, and then you point the telescope at their locations when their signals arrive, then you'll definitely find them. So, but obviously we can't call aliens. So the ideal strategy is we can call terrestrial intelligence instead of extraterrestrial intelligence. And then we ask when they will be transmitting. And then we would assume that a civilization similar to the terrestrial intelligence lives on an exoplanet. And we can point the telescopes at the exoplanet when their signals arrive. So first, what kind of signals are we looking for? So this depends on the kind of things that we can search and what we can also transmit. So along the electromagnetic spectrum, we have developed a lot of transmitters and receivers like radio, infrared, optical, ultraviolet. And we have also developed transmitters in neutrino, although that's very experimental. But we have developed detectors for these different particles. So that means we can do a lot of searches for a variety of things. So first, we're going to look at the transmitters. And what are we actually transmitting that we can detect? So this was a paper that we worked with Sophia Sheikh at the SETI Institute. So basically, we characterized all of Earth's known technosignatures and see with our current technology, can we detect any of them? So on the x-axis, it's the distance to how far we can detect things. And on the y-axis, you can see like the different types of technosignatures. So like on the very bottom, like objects on non-Earth surface and on Mars, you have to be very close to see them. But on the very top, you can see a couple of radio cases. So the first one is planetary radar, or like the Arecibo message with the Arecibo telescopes. So that was very strong, but we don't send them very often. So you kind of have to be within their beam. So you really need to be lucky to find them. But what we also found was radio case 2, which is our deep space network. So you can find our deep space network across like almost 100 light years away with our current telescopes. So, and we use the deep space network all the time. So that means if we can find its pattern, we can probably try to look for similar transmissions from exoplanets. So how do we use the deep space network? So first, the deep space network has 3 sites. Every site has a 17-meter antenna and 3 34-meter antenna, but they also have like a bunch more over the years. So they usually transmit an S and X band with an input power of about 20 kilowatts, but it can go up to 400 kilowatts, although that's pretty rare. And that means with the equivalent isotropically rated power, it's going to be a terawatt or more. So this is detectable over like tens of parsecs with the green band telescopes. So that means we can detect our own transmissions if it were on another exoplanet. So then we can look at its patterns. And the best thing is, its transmission logs are public. So we look at its transmissions, and we found that there were a different kind of spacecraft that the S didn't transmit to. So for near-Earth spacecraft, in this case, we're defining as basically closer to us than the moon. So we're not considering them because the deep space network is not used for those transmissions. And like so many other nations also have technologies like this. You can basically just like use antenna in your backyard to do that. So it's like, because the power required is very low and it's kind of omnidirectional. but also the transmission to the moon. So the DSN is used for those transmissions, but other countries also have like similar transmissions. So basically, the patterns of these kind of transmission will depend on like where the moon is and what kind of orbit it is like around the exoplanet. But transmission to the moon only account for 3% of DSN transmissions. So the last category is deep space spacecraft, which is basically beyond the moon. So it's very powerful, and NASA has led the majority of deep space missions, if not all of them. So basically, we're trying to characterize our strongest transmissions over the past few decades. So we got the transmission logs. They span from 2005 to 2025. And like prior to that, it's mostly paper-based with just a couple of years of digital-based catalogs, so we're not analyzing them. But so basically, this tells us what our recent transmissions are like. So the total transmission time is 92 antenna years, which means on average it's like 4.66 antennas are on at any time on average. And 76% of these transmissions are in X-band, which means the antenna gain is higher, so the signal is stronger for receiver. And the strongest configurations with a 70-meter dish and X-band. That means the beam is very tight, but it's also the strongest. And half of the transmissions are at 20 kilowatts-ish or more. So basically, we're looking at the strongest transmissions that our civilization emits. So we want to plot these transmissions. So first, we take the data from the DSN transmission logs. So they have things like target names, when they start, when they ended, and what their frequency and what kind of dish they use for. But unfortunately, most of them didn't have power information. So we couldn't tell the power levels of each individual transmissions. But we can just assume like most of them can be detected. So with the target names and their transmission times, we use the JPL Horizons API to find where the spacecraft are at the time of the transmissions. And then we centered our transmissions on the spacecraft location with the DSN beam. So this actually proved to be pretty hard because JPL Horizons gives you the apparent ephemeris. And that's what most of the apps do, to tell you where things are at the time you're looking for. But that's not where you should be transmitting, because these things have proper motion. And what you're seeing is like the real time minus the light time, right? If something's here, it's actually like you're seeing in the past, but we need to transmit to the future location. So actually, we have to transmit to this location 2 light times away. And another thing is, so we were thinking about plotting directions, the transmission directions in their angles from the sun. So for an observer, maybe we're transmitting like 60 degrees away from the sunlight to our Lagrange points. So we have to make sure that we're plotting these angles correctly. So for an observer, if you see an ETI, like their apparent Earth, and if a transmission hits you, that means the spacecraft is also like in front of the Earth. So, and if you're trying to figure out like if there's any angle between this transmission and the Earth, say Mars angle, you have to take account of the one-way down time from Mars to Earth with this very weird geometry. So the math is in our paper, but basically it's that if you want to measure the angle, you have to like know what the one-way downtime is, which you can sort of tell with their like orbital distances, but it's just something to keep in mind. So we plotted the transmissions in terms of the ecliptic coordinates from the sun. So this is their duty cycle, and the redder a pixel is, the more transmission duty cycle there is. So at the center of this plot is the sun. So you can see pretty dense transmissions towards the sun, but there's some orbit or structure to it. So this is actually because of our transmission to our L1 probes. So like things like Discover, which looks at the Earth, and other spacecraft that looks at the sun. So this is because if you place a telescope at L1, you can see the Earth dayside all the time, and you can also see the sun all the time. So another thing is on the left side and right side of the plot, you can see a big circle. So that's actually the JWST. So you can also see like insertion orbit on the right side. So this reflects our transmissions to our L2 probes. So as we send more telescopes to these locations, we can expect that maybe a lot of our transmissions will be towards the sun and away from the sun. So another thing that we did was we plotted these transmissions in histogram. So on the y-axis, it's the transmission duty cycle, and on the x-axis, it's basically the ecliptic longitude away from the sun. So in the middle of the plot, where x equals 0, that's towards the sun. So you can see that towards the sun and away from the sun, the duty cycle is around 4 times higher than the baseline. So basically, if you know an exoplanet's orbit, you can time your observations to the exoplanet conjunctions with its host star, whether it's the primary conjunction or secondary eclipse. That is when the planet goes in front of the star or behind the star. So this will give you 4 times the chance of detecting a signal compared to the average. And on another note, if you plot this transmission duty cycle against the ecliptic latitude, you'll see that most of our transmissions are within the ecliptic, which makes sense because we have a lot of interplanetary spacecraft. So that means we're communicating with these spacecraft, and they're along the ecliptic. And we know that most other exoplanet systems that we have seen, they're kind of like disk-like, because that's just how orbital mechanics work. So we can imagine that if an EGI lives in another solar system, maybe all of their exoplanets will have like very local inclination. So their transmissions will also be close to their ecliptic plane. So in this case, in the DSN's case, you'll have 20 times the average chance of detecting a signal if you search like with agile exoplanet system, like transit systems, and also like systems within the Earth transit zone. Like there are transit, so basically transiting exoplanets. So this will give you 20 times the chance. And we know thousands of transiting exoplanets. And with Roman launch in the next few years, we're going to know hundreds of thousands of exoplanets. So that means we're going to have so many more targets that will give you basically a boost in your chance of detecting a signal. So another thing that we did was to imagine that a system has 2 exoplanets, like Earth and Mars. And so we live on Earth, and we send a lot of transmission to Mars because we have spacecraft there. So if you plot our duty cycle across the transmission beams angle from Mars, you'll find that within a few arc minutes of Mars, we're basically transmitting at like 80% of the time. So this is a significant increase compared to this, which, in this case, the highest duty cycle is like 10 to the minus 4, which is like 10 minutes per year compared to 9 months per year. So if you look when Earth is behind Mars, you'll basically see your transmission like 80% of the time. So this is called planet-planet occultation. So you'll have like tens of thousands of times of detecting a signal compared to the average. So the chances are 70,000 if you average out to all the exoplanet planet occultations. So we think this is the best way of detecting a signal. And in our physics rendering, basically, we're transmitting some signals towards the sun and away from the sun, and also towards a lot of our solar system planets, especially Mars. So, what does this mean for our future SETI searches? So we can guess when ETI may transmit. So maybe ETI astronomers have space telescopes too. So they'll put their telescopes in their star exoplanet Lagrange points. And they may also have interplanetary probes. So they'll transmit along their ecliptic. So in these cases, we can intercept their leaked deep space transmissions. Things that if they have a DSL like ours, we can actually see them. So for the actual searches, it means that we should prioritize certain targets. So this is based on the results that 80% of DSM transmissions were within 5 degrees from the ecliptic plane. So that means you should totally target transient systems. So the target priority will be basically systems with habitable transient exoplanets or just systems with any transient exoplanets. So this last point is because if we see a transient exoplanet in the system, that means if there are any other exoplanets, they might be also they might be also close to edge on. So they might have a couple degrees of co-inclination with respect to our line of sight, but because there's already one, that means others might also be similar at a similar angle towards our line of sight. So this helps you select where to look, but it also tells you when to look. So 80% of the total duty cycle are within 0.5 degrees from Mars, and if you plot the transmissions in terms of angles from Mars. So that means you should choose to observe when two planets are in front of or behind each other. And also, you have like 2 times more likely, at least 2 times, within 30 degrees towards and away from the sun. So that means if a planet is in front of its host star or behind its host star, then you'll have a higher chance of detecting it. So as we know, NASA's going towards an optical deep space network. So this was a proof of concept transmissions that they did, which show them basically transmitting a cat video between Earth and Mars. So that was pretty fun. If you live on Mars, you can see cat videos in the future. So that means it also applies to laser SETI. So, and also in the future, we're trying to find stars that can see our past transmissions. Because if one sees the transmissions, like in contact, and if they can see our transmissions, they might choose to reply, right? So we can use star catalogs to find the stars that will receive our transmissions, and we'll find out when they might reply, so when the earliest reply time will be. So we can basically schedule our future observations from the stars that could have started the reply. So, in conclusion, for the first time, we have used real DSM transmission to quantify the effectiveness of a few SETI strategies. So a lot of these strategies they have been proposed in the past, but they were like, just trust me, this will work. So for the first time, we're using our real data to quantify how effective they are. And our research also tells you when and where you should search. So if you see one exoplanet in another star system, you should search in the exoplanet star conjunctions. And you should target edge-on systems, so like transient exoplanets. They generally will give you a higher chance of detecting a signal. And if you know 2 more exoplanets, like the TRAPPIST-1 systems, you can search in planet-planet conjunctions, and this will give you significantly more chance of detecting a signal. So this also applies to laser search because the patterns will be the same, although the leakage will be like smaller, but from our transmissions, if you use our current laser systems, there will still be leakage from our transmission to Mars. So it doesn't mean like all of the transmissions will be absorbed by Mars. So this also applies to laser SETI. So this is the QR code here on paper, and we thank NASA and NC for funding our research.
Thank you very much, Pinchen. So we now have some time for discussion. So keep your questions coming via the Q&A function. And as a first question for John from William Edmondson, does your model of signal processing assume sequential structures are part of the content? Would a raster scanned image, for example, be recovered as both image and scanning routine?
You can, if I understand that right, it's a good question, obviously, that when looking at communication itself in its natural form, it is sequential and its assumption, but also there's a capacity for identifying image structures or similar other static structures which contain information within it, and then you analyze that in a slightly different way, but they are separable.
Okay, we have a question for Pinchen from Caleb Strom. Would the short time span over which we have been using the DSN effect affect the likelihood of detecting DSN signals from other civilizations assuming comparable lifespans?
So with the assumption that we're going to destroy ourselves tomorrow, so say our DSN transmissions will be continuing for the next God knows how many years. So I think it only tells us that an ETI might send more transmissions in the future, because that's just generally how this transmission pattern works. As we send more signals to space, we need to communicate with more spacecraft. So basically, we need to build more DSN networks to support our, say, Mars missions, like if we're going to Mars. So so basically, we've only had the DSN for a few decades, and this doesn't mean that ETI will not have the DSN once they finish their evolution or after a few millennia. But it only tells us that since we're still a baby civilization, a baby space civilization, as we evolve, as ETI evolve, we should expect to see more transmissions. So I think that's the answer.
Okay. I have a question for John. So I was wondering, to what extent do we assume or define universal principles, and to what extent are we going along with Earth-centric prejudice?
I'm trying to break all prejudices. As I said, there's the slide there of the human conceit. I'm well aware that it's quite easy for us to think that everything is like us or emanates from a similar way of doing things. And you cannot assume that. And constantly trying to avoid that and come up with new ways that will cater for completely different systems. Sorry, the first part of the question, what was the first part again?
I mean, the first part is how to what extent are we assuming or defining universal principles, which comes a bit with the problem to define something as universal if we only have one example. Yeah,
and that's what universal is, an evolving thing from this point of view, is that it's universal from the samples we have. And and that with that example, then we base it on that unless we see anything to the contrary. But we have to have that obviously unblinkered way of looking at things, otherwise we won't notice what else is out there that doesn't conform. So it's very much a two-edged sword.
I mean, and at some point, that's why I use the word both assumption and definition, because at some point you assume something as universal, it becomes a definition for everything else that you're doing, and it depends on it.
Yeah. And I know there are assumptions, and it's having the wherewithal and the systems like I've been describing that can think beyond us and sense beyond us on our behalf.